Hi everyone, today we are continuing to look at rational functions. This is 13.1 and it starts on page 167. And on page 167 we see a cistern, which is like a big cylindrical barrel that's collecting rainwater. And we are looking to figure out what the function would be for h of x in terms of our rainwater based on the volume it holds. So notice here when we talk about volume of a cylinder, it's pi r squared h. So if we want to rewrite this in terms of h, we would have to divide the volume by the pi r squared, right? So basically what would happen here is our function would be h of x equals the volume, aka 25, divided by pi r squared, since they're giving us that it has a volume of 25 cubic meters. Now this is, again, a rational function, and we know it's a rational function because the top is a polynomial of degree 0, 25. The bottom is a polynomial of degree 2. So again, if we're going to call this h of x, we're just basically saying that we're going to change around the r then in this to be an x. Okay, and so this is degree 0 divided by degree 2, so that's why it's a rational function. And if we graphed this function, what we're going to notice here is that it has a vertical asymptote at x equals 0. It also has a horizontal asymptote at y equals 0. The end behavior of this as x approaches positive or negative infinity, h of x is going to approach 0 from both or on both sides. Now we also want to analyze what's going on at this vertical asymptote. So as x approaches 0 from the left-hand side, it's denoted by that little negative sign up there, we notice that, that our graph of this function, h of x approaches positive infinity, because it's going off the chart there. And actually that same end behavior is happening as we approach the the vertical asymptote from the right, denoted with this little plus sign. H of x is also approaching positive infinity. And we'll talk more about these vertical asymptote end behaviors as we move on through these lessons, but good habit to start getting into looking at those now. Now the domain and the range in terms of this particular problem is going to be greater than 0, because even though officially our graph obviously is showing a less than a negative x portion, we're not going to have a negative height for this cistern. So in terms of this real life application, our domain is changed to be 0 to infinity. Range, whether we're talking about the cistern problem or not, is going to have to be greater than 0 based on our graph. Now there is also a second type of cistern given by this function here. And we skip part A, but when they talk about the features of this graph, when we're looking at the vertical asymptote on this particular graph, we have to be careful because it's actually going to have two vertical asymptotes. Because if we took out a GCF here, really we have two pieces that are getting set equal to 0. So what we're going to notice is there's actually two vertical asymptotes. One is going to be located at x equals 0. The other is located at x equals negative 2. The horizontal asymptote on this problem is still y equals 0, or p of x equals 0, I guess you could say as well, since we're talking about p of x, not y. And then, again, the end behavior as it approaches infinity or negative infinity, our graph, we are going to see that our function p of x is approaching 0. Now this time, if we talked about the left-hand side and the right-hand side and behavior of this graph of our vertical asymptotes, as we were talking about before, they also, again, are both approaching infinity again. So we have 0 from the left, p of x is approaching positive infinity, and as it approaches from the right-hand side, it approaches positive infinity. And then that's actually also happening at our second vertical asymptote at negative 2. From both the left, it's approaching positive infinity, and from the right, it's also approaching positive infinity. So we're going to notice in time to come that these vertical asymptotes are going to have different end behaviors, but right now we're seeing them going up both left-hand side and right-hand side towards that value. Okay, now if we look here then, same idea as above, the domain and the range are going to have to be from 0 to infinity. Again, given the fact that this is a real life problem, we're not going to have an x value that's officially on this part of the graph because there isn't such thing in this terms of this problem as a negative height. So what this is asking us to do then from here is compare more graphs. So what I have graphed for us here is on this particular one, they asked us to compare and contrast a bunch of different graphs. So if we look here at each of these graphs, we're just changing the numerator to be a different value. We're noticing in all of these graphs, there appears to be a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So we keep seeing that that's consistent for both of these in number 6. So vertical asymptote, x equals 0, horizontal asymptote, y equals 0. Now if we compare just 1 over x and 1 over x squared, so the first graph and the last graph here, so we have the lighter colored one here is just our 1 over x, and then we have 1 over x squared, so kind of like our sister and problem. And what we're noticing is both of them pass through 1, 1. That's a common point to them. Both of them have a vertical asymptote at x equals 0. Both have a horizontal asymptote at y equals 0. But what we're noticing is that our original graph, f of x, has a little bit steeper increase towards that vertical asymptote than the 1 over x squared does. It doesn't increase quite as sharply. We know that the symmetry is different. This one's going to be symmetric to the origin that we talked about before. 1 over x squared, though, is symmetric to the y-axis. So these are all things that you might want to jot down for number 7 about kind of comparing and contrasting the two graphs. But again, officially, both of those are considered our rational functions. Now, if we jump back then to number 8, if we graph h of x from the first page and then 1 over x squared on this graph, if we look at these two as a transformation of each other, officially they are, our graph on the first page was represented here. So really all we did was we multiplied 1 over x squared by 25 over pi to obtain our new graph. So we just kind of changed that increase of how it's approaching that vertical asymptote by multiplying by this factor here out front. So again, that kind of relates back to what we were talking about on this last page, is that we are changing that a value to give this a different vertical stretch or shrink, and that's what we're noticing there. Now, moving on from there, they're asking us to compare yet again some other graphs and see what we're noticing about these. So I again graphed these for us on another page so that we have all of these to compare. And we have our original parent function, and then we have it compared to x over x plus 2. X minus 2 is now the green graph, x minus 4 in the denominator is the purple, and then we have the black graph. So some things that we're noticing that they're asking us about then in number 10 is these vertical asymptotes. And going back to what we've talked about before, f of x had a vertical asymptote at 0. And then for x plus 2, we actually have a vertical asymptote at x equals negative 2. Our green graph had one at x equals positive 2, x equals positive 4 for the purple here for p of x. And then last but not least, 1 over x squared plus 1 doesn't actually have a vertical asymptote at all, interesting enough. There wasn't one here. And again, looking back at our denominator here, that's basically because it doesn't have the ability to be set equal to 0 because it's imaginary. So when we're looking at these, again, it goes back to the idea we kind of discussed in the first lesson, that what's happening here is based on what's setting that denominator equal to 0 is what we're noticing. All right, at the top of page 169 then, we have this function here. And what do we think is going to happen based on this information here to our graph of f of x? Well, hopefully what you've noticed here is if we take the f of x minus 3, that's actually shifting our graph to the right 3 units, kind of going back to talking about those horizontal translations in this function notation, kind of that backwards idea. But we shifted it to the right 3 units, which means that our vertical asymptote is now at x equals 3. So kind of continuing on with this, if we look at number 12, then we have a bunch of different graphs yet again to analyze. So we have our parent function, and then we have the 1 over 2x minus 1. Now notice the shift this time in our vertical asymptote. We are now going through x equals 1/2. And if we look at the green graph here, we are shifting over here. Our vertical asymptote is now through 3. And then the purple graph, I'm going to zoom out a little bit, we'll see it's now through 6. So again, looking at that denominator, and when we set that equal to 0, each of those are now showing that shift of that initial parent graph's vertical asymptote, because 2x minus 12, when we set that equal to 0, we got x equals 6 if we would solve that. So again, we're showing that shift on the graph from using that denominator, and that again is also going to relate back to our vertical asymptote. So you may want to write that one down because that one's a little bit trickier, but what we're seeing here for 12 is that the solution to b of x minus c equals 0 is your vertical asymptote, which also means that the shift or the vertical asymptote is basically looking at where c is divided by b after we solved that. So c divided by b is something that's important to us after looking at that. All right, so if we kind of predict then with number 13, just looking at this without graphing it, how could we obtain where the vertical asymptote is at? Well, we should have looked at this and said, okay, if I set this equal to 0, I would see that the x would have to be shifted 2.5 units to the right, or to the left, excuse me, so that we would have a vertical asymptote at negative 2.5 or negative 5/2. Now also notice in here the horizontal compression factor that's happening with the x value. That value with the x out front, this is going to influence your horizontal compression when it's in the, or stretch when it's in the denominator. That's horizontal compression as well. Now, last type of questions we're going to look at is for 14. They're asking us to find the sums of each of these functions. So again, going back to our Desmos graphs, we have our original function, and then if we added the function g of x to f of x each time, what we're noticing is a vertical translation. These plus 2 and plus 5 shifted them up, the minus 3 shifted it down. So if we go back here, what we're noticing is a vertical translation based on this graph, right? So what we can see here finally, and this is kind of the most important feature to write down for today, is that these different parameters are going to shift around our our rational functions. So A is going to represent your vertical stretch, and then B is your horizontal compression. C over B, we talked about, is your vertical asymptote, or your horizontal translation. They kind of go together. And then finally, parameter D is your vertical translation. And these are the parameters, and that's just basically a constant that's going to, kind of be varied in this general form. Okay, so these are the important kind of things without even graphing that we're going to be able to tell what's happening with our function. So if we look at this last example here on page 16, it's kind of asking us to go backwards in that we're going to look to write the function based on this information of how we can transform the original graph here. So if we're reading through and we want to create this new function m of x, first thing that we see is it is translated 1 1/2 units to the right. So what this is telling us is this is our c over b value, right, is 1 1/2, or 3/2 would be your c over b. And then we have a vertical translation here using that 1/2 up. It's stretched vertically by a factor of 2, so there's our parameter a, and then stretched horizontally by a factor of 2, so there's our b value. So if we're looking to rewrite this new function m of x, in our numerator we have to consider that vertical stretch, so that's going to be our factor of 2. And then when we were talking about c over b, we said that that's 1 1/2, or 3/2 is still 1.5. So we're seeing here that b is 2 and c is 3. And that also makes sense with the fact that we have that horizontal stretch by a factor of 2, that in our denominator we're going to need 2x and then minus 3. Because again, if we're ultimately shifting this to the right, it's going to have to be a minus inside of there. And then last but not least, that vertical shift up 1/2 would be our parameter d at the end here. And our vertical asymptote then, this last piece here is where would this end? Again, your vertical asymptote then would be at x equals 3/2, since we shifted this to the right, 1.5 and 3/2. Okay. Thanks everyone. See you in class for more practice.